Okay, welcome back. So, now that have this whole arsenal of theories under our belts, we have all these theorems that back up short space functions. We have definitions of tempered distributions, operations on tempered distributions. We have now defined the Fourier transform, and we've even seen an example in terms of the Gaussian. Now, one of the big things we want to do is we want to be able to apply the Fourier transform to functions that aren't functions, or at the very least, things that aren't actually absolutely integrable with respect to Rn, say periodic functions. And so we need to come up with an alternative definition of the Fourier transform for these things. And this is going to come into the Fourier transform of tempered distributions. Now, if you remember, previously whenever we defined an operation on the tempered distribution, we actually ended up finding a way, defining it for, say, regular distributions, and then showing how we can move that operation off of the function involved in the regular distribution onto the short space function that the tempered distribution was being applied to, and then we use that movement as a general definition for that operation for all tempered distributions. So the same sort of thing is going to end up happening here. What we're going to do is we're going to take the Fourier transform of a regular distribution, and that is really just saying, and that is just making the blanket definition that for a regular distribution, the Fourier transform there is what happens when you just apply the Fourier transform to the function that represented the regular tempered distribution. Then, with a few tricks of the integral, we can move that Fourier transform off of the regular, the symbol, the function that represents the regular distribution. It's a lot of words that go into that. And we move it on to the short space function. And when we do that, what we gain is a definition for the Fourier transform of all tempered distributions, where basically we see it through the guise of this dual product. Okay, so we're going to go ahead and jump in, and that's going to give us the definition that we're looking for. All right. Okay, so let's go ahead and start talking. So we're talking today about the Fourier transforms of tempered distributions. Okay, and unlike last lecture, which was like probably a solid 2 hours, I haven't finished editing it yet. This is going to be much faster. It turns out that if you want to talk about the Fourier transforms of tempered distributions, then it's not too bad. Scrolling around real quick. Okay, so what we got? All right, so if you remember when we established all the properties of operations on tempered distributions, we always talked about regular distributions. And so first, so we'll start with the regular distributions. And the reason why is that regular distributions can be represented by a function. So we're going to let, say, f be inside the short space, and we'll consider tf, which is inside the dual of the short space. Now, if we want to talk about the Fourier transform of a tempered distribution, what makes the most sense to start off with is that we go ahead and we put the Fourier transform on f. But you can only really evaluate tempered distributions on short space functions. So why don't we go ahead and take a look at what happens when I evaluate tempered distribution acting on f hat, which we know f hat is still in short space from our last lecture. And we're going to look at what this does to some arbitrary phi for phi in short space. And let, say, phi be inside the short space. All right, so let's take a look. So we represent it like this, say tf against phi, right? And this is written as integral over Rn of f hat of x times phi of x dx. Okay, so what I'm going to try to do is I'm going to try to show you that we can move the hat off of f and put it on phi. Now we're going to end up, we have a confusion of, say, x and k here. Usually we put k in for the Fourier transform. Here we have x, but remember, k and x are both just Rn variables. So let's go ahead and expand the definition of the Fourier transform. So we have 1 over, say, 2 pi to the n over 2 times the integral over Rn of f. Let's just say, we'll put a y in here. So we'll say e to the minus I y dot x. And then we'll say this is f of y dy. And we'll multiply this times phi of x dx. Now, the only thing really to do is to try to exchange the order of integration. So we're going to have to move this guy inside the integral, and then swap integration. And so it's going to leave us with, say, 1 over 2 pi to the n over 2, just pulling out the constant. And we have the integral over Rn, and on the inside we have f of y times phi of x times e to the minus I y dot x, so none of the actual integrands changed. And since y and x are being integrated over Rn, there's no real worry about the bounds, so those can stay more or less the same. And so then we have dx dy. Okay, so what changed? So before we moved the phi of x inside the integral, because we could move it past the dy without a problem. But now that we've exchanged dx for dy, we can now move the f of y out. So let's go ahead and do that. And what do we get? So we get 1 over 2 pi to the n over 2 times double integral Rn. And now we have phi of x times e to the minus I y dot x dx. And now we have f of y dy on the outside. Now, at this point, it should be pretty clear. This is going to be the Fourier transform of phi evaluated at y. And so I can go ahead and absorb this constant, and we have this, the integral over Rn of phi hat of y times f of y dy. And that is simply Tf against phi hat. So there we go. So we see that if I want to define the tempered distribution at if I want to define, say, the Fourier transform of the tempered distribution with that is regular, I can just go ahead and write it as the original distribution times the Fourier transform of phi. That's really nice. And so that motivates the following definition. So we're going to say that the Fourier transform of a tempered distribution, comma, T, is written as, say, T hat, and when it's acting on phi, this is going to be T acting on phi hat. And there you go. We have now defined the Fourier transform of a tempered distribution. So you can prove a lot of the properties of the Fourier transform just like what you had before. So we know that we can take derivatives of tempered distributions, for instance. So you can ask, what is dA? So you can ask, what is the Fourier transform of the derivative of the order alpha for multi-index alpha? So say alpha is inside z plus n. Then you can say, well, if we want to figure out what this is, we need to first apply it to phi. And so then we have d alpha t acting on phi and hat. And then we know that this, if we wanted to figure out what the Fourier transform is, we move the Fourier transform over onto phi. So we get d alpha t of phi hat. And now we can move the derivative off of t and move it on to phi. So then we get, say, t, and then we have -1 to the alpha of d alpha phi hat. We can move the -1 to the alpha outside, and we're left with t against d alpha phi hat. Now, at this point, we can go ahead and use the properties of the Fourier transform on Schwartz functions, and so we see that we get this -1 to the alpha, t against, so we're basically going to be multiplying by x on the inside, so it's going to be, what is this, -ix to the alpha times phi, and then if I go ahead and move the Fourier transform back on t, then what do we get? We get -1 to the alpha of t hat of -ix alpha of phi, and we can take the -1 outside and cancel this guy altogether, and what we're left with is ix to the alpha times t hat against phi, right? And so therefore we can say, for instance, we get this property, t hat Fourier transform, the Fourier transform of the derivative of t hat, Fourier transform of the derivative of t is equal to ix alpha times t hat, right? And so, so this is an example of how you get some of the properties out of it. And so, and basically we use a combination of the definitions of the derivatives and properties of tempered distributions, and also the properties of the Fourier transform of Schwartz functions. And so then we were able to move these off, and now we can get properties of, the Fourier transform on tempered distributions, which are going to line up exactly the same. But yeah, so that's formally how we prove that. So then you can ask the question, what is the Fourier transform of a delta function? But before we do that, I want to talk about one abusive notation that we're going to be adopting. And so, and this will help us sort of make a guess at what this answer should be, and I'll show you how to formally prove it. So the abusive notation is that we're going to be writing t hat is going to be equal to the integral over Rn, 1 over 2 pi to the n over 2 of t of x times e to the minus I k dot x dx. And so it's going to be t hat at k. The reason why I do this, the reason why we want to do this is that we know that this formula holds explicitly when we have a tempered distribution and a regular distribution with a Schwartz space function. You get exactly this definition, which would agree with the Schwartz space Fourier transform explicitly. And then for functions that aren't necessarily Schwartz space functions, this gives sort of a way of thinking about them that might be intuitive. So that's where this abusive notation comes from. And so you can ask, what is a Fourier transform of delta? Well, then you can say, well, I'm going to say delta hat at k should be equal to 1 over 2 pi to the n over 2 integral over Rn of delta of x times e to the minus I k dot x dx. All right, now this is not even a dual for our Schwartz space, and in fact, and that's because this isn't a Schwartz space function; it doesn't decay, and this is a tempered distribution. But if we go ahead and we try to take, just use our intuition that basically whenever we take the delta against some phi, we get some phi 0, which we can also express integral over R n of phi of x of delta x times phi of x dx. And this is sort of also an abusive notation. So we're like compounding our abuses here. And so then what we would end up getting is we get 1 over 2 pi to the n over 2 times e to the minus I k dot 0, which is equal to 1 over 2 pi to the n over 2, right? Okay, so that's more or less the abusive notation, what we get out of it, but that's not formally how we show this. The Fourier transform is this. And so in order to do it more formally, we appeal to our newfound definition. And so basically what this is going to be is going to be delta hat on phi is equal to, say, delta against phi hat. And this is the same as phi hat evaluated at 0. And this, written out, is 1 over 2 pi to the n over 2 times the integral over Rn of phi of x at e to the minus I x dot 0 dx. And that's going to leave us 1 over 2 pi to the n over 2 times the integral over Rn of phi of x dx. And we want to be able to express this as a tempered distribution. And so we can write this as 1 over 2 pi to the n over 2 times 1 times phi. And that would be the same thing, where this is the regular distribution like this. Okay, so what does that tell us? Well, that tells us that the Fourier transform of the delta function is actually equal to 1 over 2 pi to the n over 2. And so we get delta hat at k is equal to 1 over 2 pi to the n over 2. And that is that is the way to show it for tempered distributions. But notice that this also agrees with the abusive notation, and so that tells us that this abusive notation is probably well-founded, and it'll lead us in the right direction. Okay. So you can also ask, what is the tempered distribution of the derivative, so d alpha of delta at hat. It's another example. But we just told you that this should be ix to the alpha times delta hat, say at k, if we'd like. And this is equal to ix to the alpha divided by 2 pi to the n over 2. Okay, not bad. Okay, now comes the slightly more interesting part. We saw before that if we convolve phi with delta of x, then we just get phi of x back, right? And that was up a couple of sections ago in the chapter here. And so then if we go ahead and use our abusive notation, we can actually rewrite the convolution of these two as delta of, say, x minus y times phi of y dx, and this will give us phi of x, right? And that's what that would be. And so, so then you can ask, what is the Fourier transform of the shifted delta function? And really this comes down to writing the delta function as using the translation and reflection operators. And so if we want to formally figure out what this is going to be this. And so we say that phi star of the convolution of the delta function and phi is equal to, say, the delta function on r tau x of phi, And then we can go ahead and move the reflection over. So we get r on delta, and then we get tx on phi, and then we can move tx over onto delta, and so we get minus x r delta on phi, right? So that's what that would be. And so then you could ask, what is the Fourier transform of, say, tau minus, here, you want Fourier transform of that guy. Okay, so what does that tell us? Well, that means we need to figure out the reflection property for the Fourier transform, and we also need to figure out the shifting property. And so why don't we go ahead and do that for general tempered distributions, and then we can apply that to the delta function. So yeah, what is, say, RT hat? First question. So what we can do is we can just go ahead and start looking at it through the guise of our dual product. So we know that this can be written as RT phi hat, and we can rewrite this as TR phi hat, right? So there we go. And that's not too bad. So then we know that R phi hat is going to be equal to, say, at k, is equal to phi hat of minus k, which is equal to 1 over 2 pi to the n over 2 times the integral over Rn of, say, phi of x e to the minus I k dot x, but then we flip the sign, dx. And so, yeah, I mean, that's what that is, right? Not sure. I mean, we could, if we want, we can say that this is phi inverse evaluate k. Right. Okay. So then we say that RT hat is equal to T upside down, the inverse Fourier transform of T. Okay. What about, say, the Fourier transform of T minus x, or let's just say T of x on tau of x on T. So that is the next question. That is going to be tau x t Fourier transformed on phi. We move the Fourier transform off, so we get tau x t against phi hat, and this is going to be t tau minus x on phi hat. And so what is this going to be? This is going to be, and so what is that? Well, we know that t minus x on phi hat. I don't remember exactly off the top of my head. Let's put a k on that, and then that's going to be phi hat on k plus x. And this is going to be 1 over 2 pi to the n over 2 integral over Rn of phi of x, pick another variable, phi of y times e to the minus I k plus x dot y dx. And so ultimately what we're going to end up having is, or dy, let's clean that up. So ultimately what we end up having is this. So this is equal to 1 over 2 pi to the n over 2 times, say, phi y e to the minus I
x dot y times e to the minus I k dot x dy. And so then this is equal to e to the minus I x dot y times phi of y. And we're taking the Fourier transform of that evaluated at k. Okay, so ultimately, what we end up doing is we're going to have this is going to be t against, say, e to the minus I x dot y phi of y. And then we can move everything over, and so then we end up getting e to the minus I x dot y times t hat. Think of that in terms of y times phi. Or, yeah, I think so. Might get my variables screwed up there. I think that's right. Just all these k's and x's and y's just confusing me. But yeah, that's the general idea. Okay, so now we got that far. Now let's see if we can go ahead and apply this to our delta function. So what do we expect to see? So we have the integral of, so we're trying to figure out what the delta, oh man, it's gonna get confusing, all these x and y's and whatnot. I'll say minus h. So we're trying to figure out what the Fourier transform of this guy is. And so we know that coming from delta of x, we can get to delta, say, of x minus h, actually just by taking tau of h. So maybe I overcomplicated it a bit, but now we have a... Alright, so that's what we get. So now we're taking the Fourier transform of this guy. Sorry for the confusion. And then we get delta here. And so then this is going to be e to the minus I, say, k times h times, Fourier transform of the delta function. And so it's going to be 1 over 2 pi to the n over 2 times e to the minus I k dot h. Alright, not bad. And is that what we'd expect to find? Yeah, more or less. So if we wrote this as delta of x minus h times e to the minus I k dot h over Rn, 1 over 2 pi to the n over 2 using our abuse notation, d, oops, not k dot h here, that should be k dot x, and so dx. Then the only non-zero contribution of this guy is going to happen at h, and so then this should be equal to 1 over 2 pi to the n over 2 times e to the minus I k dot h. And so, yeah, that's what we'd expect. Okay, so good. Okay, so I'm going to call it here, and thank you for listening.
Okay, so welcome back. So we saw how to apply the Fourier transform to tempered distributions this time. And there was a few standouts that we saw. Is one of them was that we looked at the Fourier transform of the delta function, which ended up being just a constant. Now, this is actually a very significant result, and it helps us preview what is going to be called the uncertainty principle with the Fourier transform, and that being that you can't have good localization in space as well as frequency at the same time. The Fourier transform of the delta function is a really extreme version of that, where we view the delta function, which isn't really a function, but we kind of have an imagination of it as being like a sort of like infinite peak at 0 and flat everywhere else. So it's extreme localization in the, say, state space or in time. But when we go ahead and take this Fourier transform, we get a completely flat constant function, and that has no localization because it's very, very spread out. We can see it's balanced between localization and through the, say, the Gaussian, for instance. We saw that one mound will turn into another mound through the Fourier transform, and it turns out if you make one of those mounds really peaky, the other one will get really flat. And so then you can even see this happening if you take a Gaussian approximation of the delta function and make the Gaussian steeper and steeper, but keeping an area of 1, that'll give us a delta sequence, and then you'll see on the other side that the Fourier transform is going to flatten out as you go. So then that sort of previews what is going to be called the uncertainty principle for the Fourier transform, which is exactly the same as the uncertainty principle that you see between momentum and position out of quantum mechanics. In any case, here we're going to stop, and we'll talk about the uncertainty principle and other things in future lectures, but that gives us a nice little preview. In any case, thanks for listening, and I will catch you next time.